In this video, I again want to talk about hyperboloids, but this time we want to talk about hyperboloids of two sheets. Now, here's a basic one here. Minus x squared minus y squared plus z squared equals 1. Notice that there are all of the squared terms. There's an x squared, there's a y squared, there's a z squared. And in this case, there are two negative signs out in front of them. Now, I have to be a little bit careful. I have a 1 over here. I set it up so that it's essentially x squared, sorry, minus x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. If it's something other than 1, I'm going to divide by it and get a 1 right there. Now, I say that because this equation right here is actually equivalent to x squared plus y squared minus z squared equals minus 1, right? If I just multiply both sides by minus 1. So just looking at these by themselves and saying, oh, 1 minus sign, this will be a hyperboloid of 1 sheet. 2 minus signs, this will be a hyperboloid of 2 sheets. No, it doesn't quite work that way. Get a 1 right here first, so then you know, once this is a 1, right, that's a minus 1. Multiply by minus 1, that would give you 2 minus signs, and it'll turn out this is a hyperboloid of 2 sheets. Again, let's take a look at, I say again because we did in the last video, let's look at the traces. In the xy plane, I have z equals 0, and this looks like minus x squared minus y squared equals 1. This is impossible. No, we can't do it because this left-hand side is always 0 or negative, right? If you plug in 0, 0, that'll be 0, but it's not equal to 1. If you change x or y to anything other than 0, then this is going to be a negative number and certainly not equal to 1. So this never happens. However, if I were to plug in, say, z equals 1 or minus 1, then this looks like minus x squared minus y squared plus either 1 squared or minus 1 squared, but either way it turns into a 1 equals 1, which then looks like minus x squared minus y squared equals 0, which if I could multiply by minus 1, x squared plus y squared equals 0. This is now a circle of radius 0. So up here at z equals 1, this is a circle of radius 0. Also down here at z equals minus 1, this is a circle of radius 0. Plug in something bigger than 1, say z equals plus or minus 2, then I've got minus x squared minus y squared minus 4 equals 1, or, so plus 4, right? Because that's plus right there. So I've got minus x squared minus y squared equals negative 3, or x squared plus y squared equals 3. And that is now a circle of radius square root of 3. So by the time I get up to 2 here, I have a circle of radius 3 in that plane, z equals 2. Also down here at z equals minus 2, I've got a circle of radius 3. And perhaps you can see that the bigger value of z I put in, absolute value-wise, right, plus or minus, you're going to subtract this over, it'll be a much bigger negative number. It'll be, once you square it, it'll be positive, but when you subtract it from 1, it'll be a big negative number. But then everything's negative, so multiply everything by minus 1, and you'll be getting circles of bigger and bigger radius as you go up. So it starts off at a small circle and gets bigger and bigger, and you get these two pieces, one of them opening upwards, one of them opening downwards. And this is called a hyperboloid of two sheets because there are hyperbolas in here. I've been looking at just z equals a constant. Let's take, for instance, in the xz plane, so let's let y equal to 0. Then this is minus x squared plus z squared equals 1. This is an hyperbola in the xz plane, and this time it opens upward and downward like that, because it's okay if x is 0, so you can hit the z-axis here and here, but you don't want z to equal 0, because then you'd have minus x squared equals 1, which can't happen. So it doesn't hit the x-axis, it just hits the z-axis. And that's, so if this is the x-axis here and the y-axis and the z going up, that would be the hyperbola that comes down to that point and then comes up on the other side, and likewise comes up here and then down on the backside there. Or if I look at the yz trace, so let x equals 0, you're looking at minus y squared plus z squared equals 1. Oops, z squared equals 1. So this is a hyperbola going this way. Okay. So the traces look like hyperbolas in two of the coordinate planes, and they look like, well, either nothing or circles in planes parallel to the z-axis. This is what's called a hyperboloid of two sheets. I want to take a look at a computer image of this. So here is precisely the one we had, minus x squared minus y squared plus z squared equals 1. And this is the hyperboloid of two sheets. Okay. Like ellipsoids or hyperboloids of one sheet, you can stretch and squeeze this by replacing the x by x over a, or the y by y over b, and the z by z over c to get corresponding stretches of a, b, or c in the x, y, and z direction. So in general, it looks like this, and if I change one of these things, it's going to stretch things in one direction or another. So changing b to b2, now that stretched my basic hyperboloid of two sheets in the y direction. It still would look exactly the same if I look down the y-axis and I'm seeing only the x and z. But when I look at it this way and seeing y and z, right, it's definitely stretched in that direction. Okay. Dealing with the equations is the same thing as dealing with ellipsoids. If you want to find the center, you're going to have to take the equation and complete a square and whatnot to get it into this form, into the x minus h squared over a squared, y minus b squared over c squared. And because there's two minus signs here, after you've already gotten a 1, it turns out that's a hyperboloid of two sheets. And because the z here is the odd one out, minus, minus, and plus, this thing is centered on the z-axis. If it was plus, minus, minus, where the x is the one with the plus sign, then it would be tilt this whole thing down to center it on the x-axis. And likewise with the y. Now, I want to take a look at another version of this, which I have here. So here's my hyperboloid of, is it of one sheet or two sheets? Here's the equation. It's the same, x squared over a squared plus y squared over b squared minus z squared over c squared. This time equals t, where I'm taking here, for example, a is 1, b is 1, and c is 1. Okay. But the t here, I'm going to use as an animation parameter. Okay, so t is going to run from -2 to +2, and when I click on this, watch what happens. The hyperboloid of two sheets turns into a hyperboloid of one sheet, and right in the middle there's a spot. I missed it. Let's try again. Right in the middle there's a spot where this is a cone. Okay, let's take a look at what's going on there. So in this animation, the very first frame has the equation x squared plus y squared minus z squared equals -2. Now, in order to see what that's supposed to be, I need to divide both sides by -2. So I'm looking at x squared, so let's say minus x squared over 2 minus y squared over 2 plus z squared over 2 equals 1. So there's two negative signs in this, and this is a hyperboloid of two sheets. It will be, something that looks like that. Right down the middle will be the z-axis. Okay, and a couple of things here. The distance up and down from the xy plane, up and down is the square root of 2. As I change this now to say -1, x squared plus y squared minus z squared equals -1, dividing by -1 gives me x squared, actually gives me minus x squared minus y squared plus z squared equals 1. Now, rather than being up and down 2, it's only up and down 1. So this is a hyperboloid of 2 sheets that's got the 2 sheets a little closer together. And as we keep changing that number closer to 0, say x squared minus y squared minus z squared, sorry, that was plus y squared, let's say equals, -0.1, then that turns into a minus x squared over 0.1 minus y squared over 0.1 plus z squared over 0.1 equals 1. And now these are really close together until you get to the point where you're plugging a 0 in. X squared plus y squared minus z squared equals 0. I can't divide both sides by 0 to turn it into the form that I like with a 1 right here. This is, in fact, a cone, and we'll talk a little more about cones in the next video. But the point here is that hyperboloids of 1 sheet and hyperboloids of 2 sheets are very closely related based on the number over here that you divide by before it becomes a 1. Right? With these negatives here, even though this looks like I've got a plus plus minus, that might be 2 sheets because that's a minus. When I divide, it becomes minus minus plus, and I have a hyperboloid of 2 sheets. Once I then get to positive numbers, x squared plus y squared minus z squared equals +1 over there. Right? This is now a hyperboloid of 1 sheet. The intersection with the xy plane is now a circle, and the hyperboloid opens this way as 1 sheet. That's what that animation is showing. This is where it's up to +2. So negative values of t, dividing so that it looks like 2 sheets, you get to 0 in there where it's a cone. And then with plus signs here for t, it's like here, hyperboloid of 1 sheet. Okay. Shows a nice transition. Everything that we do with the other ones in dealing with the equations, you would do here as well. Completing the square to find the center and all kinds of things like that. The determination of 1 sheet or 2, you have to get it into this form where the thing over on the right-hand side here is positive. In fact, 1 would be the best one. And then you can see how many negative signs in front of the quadratic terms, and that'll tell you whether there's 1 sheet or 2 sheets.